Hi everyone, welcome to another video lecture. Today I want to talk about the hidden Markov model. I spent my, I would say 4 years, 5 years of graduate school investigating the benefit of hidden Markov model, using hidden Markov model in various domains, especially in educational system. And today I want to actually share my experience about hidden Markov model with you guys. So there are lots of videos and books written and articles written about hidden Markov model. I have also published a couple of articles about hidden Markov model and how to model educational system using HMM. But today I want to talk about the important stuff regarding modeling and some of the important concepts regarding implementation of HMM. I have implemented HMM in Python, MATLAB, and R language, the most complete implementation of HMM I've seen in the internet. I have shared the Python version of that in my GitHub, which I'm gonna go over that in the last slide of this PowerPoint presentation. But before that, I'm gonna give you some introduction, some background, and then the modeling phase of the HMM, and then the implementation. So what's the purpose of this video though? There might be other videos available in the YouTube about HMM. There might be articles and books about HMM. The purpose of this is that when I study HMM, okay, there are a lot of theory behind that, forward, backward algorithm. There are a lot of mathematical um, articles. They are full. Internet is full of them. But if you want to model that, there is really nothing in the internet tells you how you can model a phenomena using hidden Markov model, which is extremely powerful technique. First, I was actually very confused. Then I had to actually dig into the data set myself, and then I start asking a question: what is the hidden state? What is the observation? How do I know what should I feed to this packages and all this problem? So today I want to go over all this stuff to make sure that you all have a good grasp of hidden Markov model. All right, so let's start. And all right, let's just talk about the introduction first. What is HMM? HMM is the simplest or one of the simplest version of the dynamic Bayesian network. So let's try here, dynamic Bayesian network, dynamic Bayesian network, and or DBN in short. And I have a video lecture about the Bayesian network. I will put a link in the description if you want to check that out, because I had a package called tsBNgen. tsBNgen. This package is about generating synthetic time series using the arbitrary structure of a Bayesian network. Now, the HMM, the structure looks like this. I continue. All right. So it's called O1. These are observation. O2, O3, right? O4 all the way. And this is called S1. Let's say it's S2, S3, and S4 all the way. All right. Great. Now, so these O's, these OIs, they are called observation. And these are what we observe, right? What is given to us. This S, the SIs, called they are the hidden states. The hidden states. These are what we are trying to infer. All right. So here, so this is the structure of the hidden Markov model. Now let's talk about these different uh, assumptions that we have. One of them is a Markov assumption. So this is not only new for HMM. This the Markov chain also has this assumption. A hidden Markov model is the extended version of the Markov chain, right? Given that in Markov chain, the states, this S, these SIs are observed. In hidden Markov model, they are not really observed. So it's a doubly a stochastic process, right? But for now, we don't want to get to the mathematics of HMM. And now, what does Markov assumption says? What it says is that condition on the present, the future, and past are independent. So that's what it says in high level. In a context of HMM, what it means is that probability of um, Sn given Sn minus 1, Sn minus 2, the entire history all the way to S1 is nothing but probability of Sn given Sn minus 1. So if you give me the full history, I don't really care about that. All I care is the most immediate observation. So take this Sn minus 1 to be the present, and this is going to be the future, right? And anything else before Sn minus 1 or n minus 1 time point is going to be the past. So what HMM says that the future is only dependent on present. I don't really care about whatever happened in the past, all right? That's very important Markov. This is called Markov assumption, right? But the next one is the something we call independence of observation given states. All right, so this is, you can explain this one using D separation. So I try my best to explain this concept. What it says is that probability of, for example, OI given, I don't know, O1, O2, all the way OI minus 1, S1, S2, all the way to Si is nothing but probability of OI given Si. What it means is that if you condition on the state that is connected to that observation, right, then in a sense that observation is independent of any other observation and any other states. What it means is that look at this Si here. Look at O1. I'm looking at this time frame, right? O1, if you condition on S1, what it means in a context of this separation is that when you condition on this, it means that you're blocking the path, right? So when you condition on S1, you're blocking this path, right? So any path from O1 to any other state or any other observation has no choice but going through S1. So if you condition on S1, you're blocking the path. And in a sense, when you're blocking the path, this means that condition on that O1 is independent of any other state and observation. So that's what this one says, right? All right. So this is making the mathematics of HMM significantly easier. And that's why HMM is very attractive, because the mathematics of that actually, or there is a kind of closed form solution for finding the number of, for finding the optimal parameters in HMM. This is due to these two assumptions that we have. All right, great. Now, let's talk about the background. So this background here is that what is HMM trying to answer? HMM in general is trying to answer these three questions: the likelihood, the decoding phase, and the learning, right? So in the likelihood phase, what is the likelihood? Likelihood is that when you have a set of data, like a data sets, you are asking yourself, okay, and you have a parameter theta you want to estimate. During the likelihood, you say that given this data that I have, that I observe this data, right, what parameter is gonna give me, is gonna maximize probability of observing this data? That's what the likelihood pretty much is, right? So what likelihood does is that it's actually pretty much it's asking these questions, right? So now we need to see what is the likelihood in terms of the HMM. So define the HMM parameters to be lambda to be A and B. So for now, I haven't defined this, so I don't want to talk about the mathematics of HMM. But this B, right, is going to be the observation matrix. You can read more about that in the internet. And A is the transition probability matrix. right? So in the likelihood version, or in the likelihood part, what we are asking ourselves is this. We are asking ourselves again, like any definition of the likelihood, we have set of observation or data set, which should be denoted with O, right? This O can be like O1, O2, like what I had in the last slide, all the way to O1, right? So in the likelihood version, we are trying to find this probability. We are trying to find the probability of this observation sequence O given the parameters, right? So that's what the likelihood is. When you have a set of data points, right? When you're asked to calculate the likelihood of these data points, you have some parameters. You're trying to find the probability of these data points you get given the parameter you have. And then what I defined initially was actually maximum likelihood. Maximum likelihood, you're asking yourself, you know what? I have these data sets. I observe them. What are the parameters that maximize probability of observing this data? So this is actually a definition of a likelihood. This is one of the things that HMM can be used for. I'm going to talk about the next slide about the modeling, and I'm going to go over all this interesting stuff that you can do with HMM. Now, the decoding phase, this is usually done through the Viterbi decoder. Although Viterbi is a maximum likelihood decoder, ML decoder. I have a set of videos about maximum likelihood versus map. It's the estimation series that I have. I explain what these stuff are, right? I will put a link in the description if you would like to check them out. But Viterbi decoder is a maximum likelihood decoder. Also, we have a map decoder as well. But mainly in HMM, Viterbi decoder is used, right? So what's the question that we are trying to answer? Here, we are trying to answer, you know what, high level, we have a set of observation, O, which is O1, O2, all the way to ON. The question that we have is that, okay, I have this observation. What's the most likely sequence of hidden states corresponding to that? All right, so I have O1, O2, ON, and what I want to find is this S1, S2, all the way to SN. What's the most likely sequence of observation? Look at the internet. There are lots of equations and stuff for that. You can go over that. Of course, they all be done. This decoding also is a Viterbi decoder, can be coded or formulated using dynamic programming, which is an efficient version of recursion. But what here is important is a high level. You understand first what we want to do. We are given observation. We want to find the most likely sequence of hidden states. All right. Now, what's the learning? As the name suggests, is that we are given the O, the observation, and also we have a sequence of hidden states. We are asking ourselves, so these are the input. We are asking ourselves, what is this A and B? This transition probability matrix and this observation probability matrix. And also there is another one that also is the initial probabilities or the prior probabilities. Usually it's denoted with P, right, pi. And so that's a learning phase. Now the learning phase in HMM is done through expectation maximization, which is an iterative process. In context of HMM, it's called Baum-Welch. Please comment down below if you would like the video about EM or Baum-Welch, right? We can go over that as well. But Baum-Welch or EM algorithm in HMM, in the context of HMM, is done through forward-backward. And they are also done using dynamic programming, implemented dynamic programming. Decoding phase also is done through dynamic programming. There are lots of material about this stuff in the internet, but it's very important to understand high level what we want to do. This was a lack of, I believe, resources when I wanted to do this stuff back in my graduate studies. And I was always confused, as most people, they know the mathematics of HMM, but they didn't know what should be done, why you should use HMM, or for what problems HMM should be used. All right. Now let's talk about modeling with HMMs, which is very practical and very important phase. Now, when you're modeling with HMM, usually what you're looking for first is that what type of problem HMM can be used for. I will give you an example of a couple of domains that HMM can be used. First, when Professor Rabiner actually talked about HMM in his very famous paper, he used it actually for a speech, as that was his research. And HMM first was used actually in speech processing. It was very popular in speech. Now, HMM can be used in medicine and education, which I spent my entire research, PhD for the HMM in education. The research was mainly in causal inference, but I have done also HMM or probabilistic graphical model in education. For that, as an example, you can, for example, I didn't do this, but you can, for example, take the exam, for example. You can take the exam scores as observation, and then the hidden states will be sequence of the student's mastery level as they go through the exam score. For example, if they are learning or not, you want to see if these exams are actually beneficial for students or not. That can be, for example, how you can use HMM in education in a very simplistic way. But then I wrote time series and sequential modeling. So HMM can be used in NLP, natural language processing, for example. Anytime that you have a time series or sequential data, and if you think that you have some sort of a hidden state, then you can use a HMM for that. So, for example, the example that is very common in the internet is that, so let's say you want to estimate the season of the year. You want to see whether you're in the fall, winter, spring, or summer, right? So this is the hidden states. You don't observe, you don't know. You want to see what season of the year you are in. What you observe is the number of ice cream that somebody is how many ice cream someone is eating per day, for example, right? So you're gonna, for example, see, I don't know, one ice cream, one, the sequence is 10, 20, as the weather is actually getting warmer, right? So this is a sequence of actual observations that you have, right? So here somebody is asking you, hey, based on this observation, can you estimate what's the season of the year? All right, so there are a couple of things you have to pay attention to that. I make sure I talk about that right now. One of them is how much data you have. The other one is what's the nature of the data, right? So size of data, nature of data, right? So the thing is the size of data, hidden Markov model can be used when the size of data also is small, when the number of observation is small, right? So when I say number of observation, this sequence that you see is considered as one observation. Another sequence 2 to 11, 21 is another observation. 3, 4, 8, 35 is another observation. So here we have 3 observations. Hidden Markov model was a paper I wrote about the comparison of HMM, and LSCM. In that paper, I showed that actually using simulation that HMM can be very, very strong when the number of observation is small, right? So that's one thing. When the number of observation is small, HMM can still be used. Now, another is that the nature of data. So if the nature of data, if the data is sequential or is it cross-sectional? Cross-sectional means what you see for the classical machine learning model, like random forest, like linear regression, means that the data is for one point at time, like a snapshot of one point at time, snapshot of one point at time. Now, HMM is mainly for sequential. It's actually used for sequential data, time series data, ordered in time. There is some sort of order actually. All right. So HMM is for sequential. Now, another important thing is that this is very important is whether you have supervised or unsupervised. Now, supervised or unsupervised, HMM can handle both. It's very few the models that you can find that can handle both of them. Like the supervised version, you have LSCM or recurrent neural network family per se, deep learning family. Then you have a conditional random field, which you call it CRF, and then HMM. There are more actually. There's one maximum entropy model as well. And so the thing is that only HMM can handle unsupervised. I mean, so RNN through autoencoder can call it as unsupervised, but it's not a problem of modeling here. You usually use for dimensionality reduction or outlier detection. CRF is purely supervised. So that's where power of HMM actually comes in handy. Most of the titles you find in literature is not labeled, right? This is it requires a lot of effort to label the time series. So that's why you use the HMM for, right? So that's actually something very, very important that I want to point out, that HMM can be used for the unsupervised as well. Another thing that is very important here is that for the HMM, you need to have this notion of a hidden variable. If your goal is purely to predict or forecast the future value of a time series, I wouldn't really recommend you to use HMM, right? So the thing is that HMM is mainly used for the classification of the time series or segmentation of the time series. So you want to segment the time series to fall, winter, spring, summer, to 4 segments across time, right? Across time, you want to do that. Or some people call this problem actually as a change point detection. Some people call it as a change point detection. Change point detection, right? Now, if you want to do forecasting of the future value of time series, I wouldn't really recommend using HMM. If you have a univariate time series, you can use ARIMA, fall, winter, like a simple exponential smoothing, double exponential smoothing, so like this whole winter problem. Or you can use like RNN type network deep learning, like LSTM, GRU, right? So you have other options if you have time series forecasting, right? If you have a multivariate, again, RNN can be used. You can use VAR, vector autoregression. If you have seasonality, you can use SARIMA, right? So I wouldn't recommend using HMM for that. You can use that. If you need help with that, I can help you. If you have a question or comment, you can put it, ask your question under this video. I will tell you how to use HMM for that. But I don't think it's gonna work really well, as HMM is not the primary means to actually perform time series forecasting. All right, so the way the modeling is done is that usually, as I explained in the last slide for this likelihood decoding and learning, is that you actually provide this observation, right, which can be anything in terms of sequential observation to the HMM. And the first phase is that usually you estimate this parameters. This is for unsupervised learning. That is the Baum-Welch I told you is actually for unsupervised learning problem, that the parameter estimate through expectation maximization. If the problem is supervised, means that you have the actual states, then in that case, the estimation A, B, and pi is actually very easy. It's just a counting problem. And it's like a mapping problem, it's like a supervised problem, just to find A and B and pi based on that, right? And then you can use a beta V, actually beta V decoder, and to find the sequence of hidden states for the testing data. For training, you already have these states, right? But the HMM, the power is coming from unsupervised learning problem. All right, so you feed this one to your packages. I will explain about the package that I developed, and then you can get a sequence of hidden states, and based on that, you can actually go ahead and segment your time series. All right. Now, implementation. I wrote the package in Python. Then I wrote the same version of first I implemented the package in MATLAB. Then I implemented the same package in Python, and then I did it in R. They are all successfully implemented. They can all handle discrete hidden Markov model, discrete HMM, and continuous HMM. All right, so what are they? Discrete. So first thing first, in HMM, in hidden Markov model, hidden states are always discrete. Otherwise, if they are continuous, then you are dealing with a Kalman filter. So Kalman filter is like a continuous state HMM, or HMM is a discrete state Kalman filter, more or less. So the discrete version is referred to the discrete observations, right? Means that the observation are like 1, 5, 4, 3, and continuous means that 26.5, 48.9, right? So the discrete observation or discrete HMM, the observation are modeled through multinomial distribution, multinomial. And in the continuous version, the observation usually are modeled through a mixture of Gaussian. All right, great. So the packages I developed can handle supervised, unsupervised, continuous discrete. It's very, very complete. Now, I released the Python version since a lot of people use Python, and the Python package, I name it AutoHMM. Why did I name it AutoHMM? The package is available on my GitHub. I put a link in the description. The reason why I call it AutoHMM is because, first of all, it has support for continuous discrete because of this. So automatically find the number of hidden states. So number of hidden states in HMM is actually a pretty big deal. You don't know how many hidden states you have. You have to give it to HMM. You don't know how many hidden states you have. If you have a supervised learning, of course, the number of hidden states already, you can infer it from data. So this package, what it does is that you specify the maximum number of hidden states you can imagine, like 10. Specify the max number of hidden states. Max number of hidden states. And then what's going to happen here is that this package is giving you the optimal number of hidden states through AIC and BIC, through Akai key information criteria and BIC, Bayesian information criteria, right? So I think I had a support for the cross validation. So I don't know if actually I include in a Python version or not. But the AIC and BIC usually work great here because we are penalizing to have a lower number of hidden states usually, right? Cross validation, it seems that is actually picking up the larger number of hidden states. Now, this will be done automatically for you. Find an optimal number of hidden states, and then mapping a hidden state. So the hidden states in HM usually don't mean anything, right? So in the context of educational system, so let's say you want to find the student's mastery level, you get 1, 2, 4, 3. The computer doesn't know 1 is good or bad, 4 is good or bad, right? Then you have to map it to the, based on whatever criteria you have, that 1 is the highest hidden state, 2 is, I don't know, 1 is the lowest one, 4 is the highest one. This package also automatically does this for you. So there is a flag in the package that actually tell you whether you want to go with the highest or you want to go with the lowest. So this package also does this for you. I consider this package as a really complete version of the most complete implementation of HMM. I used the actual Python packages for the actual implementation of the HMM inside my package. So HMM learn, this is based on the HMM learn. So it's written on top of the HMM learn. And if you need the R version or MATLAB version, I will hopefully release them actually very soon. And I try to actually optimize them in a sense that they all give me the same result, more or less. If you want more information about this, I have the HMM versus LSTM paper, which is actually currently in archive, and the predicting HMM for predicting student performance. That one is available in archive, but also is published in IEEE. And also, I have the documentation about this auto HMM in Medium, as a Medium article, which I put a link in the description for that as well. But if you have any question or comment, please let me know. And hopefully this video actually was helpful for you guys. Please let me know what topics you are interested. I talk about that next. And thank you so much for listening.